Today's video, we're going to just talk about the named alpha carbon reactions, the ones that you need to know by heart, by their name and the reagents that they use, and the products that they're going to form. The first one that we're going to talk about is the Klein reaction, which simply put is an aldol reaction using an ester enolate. So in the past video, we talked about how you can use aldehydes and ketones, deprotonate them to form their respective enolates. But with the Klein, we're always going to use an ester. So some carbonyl ester with an alkyl group over here. And you can have whatever you want as a substituent here, but when you deprotonate it, we always are going to use the same substituent off of our base. So what I mean by that, for example, is I've got an ethyl group coming off of this, and so the base that I'm going to use, it better be an ethoxylate ion, because of course, this base is at some point or another going to attack this carbonyl. And but when it does, it's going to just pop this leaving group right off and replace it with itself. So we never actually change the structure of our molecule here. But eventually, the molecule, the base, is going to deprotonate this acidic proton here, and at some point form the enolate ion that we want. So it's important that we make sure we use the right base for the job in this instance. So if this instead was, a methyl group, then we'll just go ahead and use methoxylate. Deprotonate it. A key point with these Klein reactions is to recognize that they're reversible condensation reactions, just like aldol condensations. But whereas an aldol condensation would form an alpha beta unsaturated molecule, a Klein condensation, it will not form this alpha beta unsaturation. And this is due to the fact that when this hits itself, we hit the enolate right here, pop this off, the product formed is going to be a structure within this general realm, and it's not going to have an opportunity, because of that leaving group leaving, it never actually forms the alcohol, and consequently we're not going to eliminate and form water, and in turn we don't form this alpha beta unsaturated pi bond right here. And what we mean by unsaturated, if you recall, is an alkyl chain that is fully saturated has hydrogens in every possible position that a bond can form. If at any point we lose some of these protons to the form of a double bond, for example, then we would say that this is an unsaturated carbon and an unsaturated carbon here. And in a carbonyl system, if it's the alpha and beta positions, well, that's not really a beta, is it? In the alpha beta positions, if that's unsaturated, we call this an alpha beta unsaturated system. It should be noted that we've just made a fairly acidic proton even more acidic, and so this base, of course, is going to come and deprotonate it. So we should mention that there's going to be some type of workup here, acidic, in order to keep this in the protonated form. So next up on the docket is the Dykman or Dykman cyclization, and it simply put is an intermolecular Klein. So don't forget our rule where we need to have about 5 atoms apart between our nucleophile and our electrophilic spots if they're on the same atom. And consequently, we're always going to form 5 and 6 membered rings usually. Obviously there's outliers and bigger rings, but these Dykmans prefer to form 5 and 6 membered rings. Here we've got, if I count up, we've got 1, 2, 3, 4, 5 atoms away from where this enolate's going to form if we use a base here to deprotonate it. And we're going to deprotonate this position right here. And that is going to cause it to come over here and hit this one. And so this is going to be a 5-membered ring. And you can kind of imagine how that's going to form, where we always keep the nucleophile intact, and it's hitting this guy right here, which is in turn going to do the whole up and around and kick off the leaving group. And because it's intermolecular reactions always form rings. It should be noted that a Dieckmann is always going to be an ester enolate and an ester group. Theoretically, you could form the same structure putting some other leaving group on here, like a chlorine or a bromine here, but eventually this is going to come in and substitute that. And so the Dieckmann synthesis, by definition, will have an ester group as well as the ester enolate. Then we have alkylation, which is, as it sounds, we're going to add alkyl groups to our alpha carbon positions. And we're going to go back to our kinetic and thermodynamic idea here, where we have options of where we put these. So if I want to put the alkyl group of choice into, say, the less substituted position, that's going to require us to go through a kinetic pathway. As you might recall, you're going to have 2 pathway options. You're going to have one that's going to have a bump right here that requires less energy to get in, but you get less of a payoff. Whereas you're going to have the other option where it's going to require a little bit more energy to get into, but the payoff is greater in the fact that you're with a more stable molecule. And that's the idea behind these different temperatures. You know, you put in more heat and you're going to be able to get over this hump better in order to form the more stable product or the more stable intermediates. Whereas if you have less heat, you're not going to have the opportunity to get over this hump, and it's just going to slowly make more and more of this kinetic product, or the one that's less stable. And notice how we use LDA for this situation. LDA is favorable to this position right here, because if you recall, LDA is this large and in charge base right here, which is big and bulky, and it's not going to want to go right here. It's going to want to deprotonate the less substituted position for less steric interference, and it's always going to get this side. So if you want to go the kinetic route, make sure you use a big bulky base, a strong one as well. So LDAs are a perfect candidate for this here. And of course the product form is going to be this, what we already have, but we're just going to go ahead and alkylate this position right here with the alkyl of our choice here. I'm just using ethyl bromide, and of course I'm just going to add an ethyl group over here, but you can go ahead and add whatever you want. This is very synthetically useful, because if you can just add a carbonyl here in your synthesis, you can later remove it, and you've added an alkyl group to a position of your choice. If we jump over here to the thermodynamic product, it's pretty straightforward. It's just the same thing, except we've now added another alkyl group to this position instead. And again, note the base, we're using NaH because it's going to deprotonate the more substituted position, because there's absolutely no sterics involved with that base. Next up is the malonic ester synthesis. The key ingredient of this is the diethyl malonate, this very stable enolate ion that we can use. And it's always going to go from some alkyl halide to that same alkyl group now attached to 2 extra carbons, 1 and 2, in a carboxylic acid form. The method that it uses for this is, of course, we're going to deprotonate this and turn it into the enolate of what we want. And this is going to come in acting as our nucleophile and substitute here in a very basic SN2 fashion. And we're going to form the diethyl malonate with the addition of this alkyl group of our choice. And so it's interesting in that we often say that this is becoming this. In reality, we're turning this into this using this reagent. That was a lot of thises right there, and kind of a silly way to describe it. But now hopefully you noticed we haven't quite yet reached this stage yet, and we're going to drop this in acid and form the carboxylic acids And we're going to go ahead and form the carboxylic acid version of this same molecule. Keeping the R group that we have added. Then there's this hidden step. How do we get from here to here? This is what's going to be kind of new to you, but it's simply heat is the reagent here. And it's going to do what we like to call a decarboxylation. And as it sounds, this is the loss, as indicated by this D, of carboxylic acids. We're going to cut off one of these. It doesn't really matter which. And so let's take a bit of a detour over here to how that decarboxylation works. So what I've done is I've taken that same molecule and I've twisted this sigma bond so that it's easier for us to understand what's going on with these arrows that we're about to push here. And let's use blue for this mechanism here. What's going to happen is we have an opportunity to form a very stable product. We're actually going to form CO2, which is just going to bubble off in its stable molecular form, and as well as a singular carboxylic acid. And that incentivizes this to move forward. Of course, we have to put in that heat in order for it to move over the hump of these strange transition states. The method that it uses is we're going to use this abundance of electrons we have in this pi bond here to come up and grab this acidic proton. That's going to cause this bond here to move down, and since we've broken this octet, we need to move some electrons here somewhere. We could bounce these up onto the oxygen, but you might recall we actually broke an octet here and formed a carbocation. And so we have an opportunity to fix that while also fixing this broken octet that we've just formed. And that's going to form the products that we want. First, I'm going to draw what we've formed right here, which is that CO2. You can see this O is being double bonded to this central carbon right here, which is then double bonded to that oxygen, which is namely CO2. And over here, we've actually formed an enediol. I don't know if that's what you'd actually call it, but it sounds about right. And with that R group on there, of course, still. And as you know from enols, they sure do love to tautomerize. They're big fans of the old tautomerization. And we're going to reform that carboxylic acid. So that's what happens in this step right here. You can see how I've drawn that same structure. If we compare the two, I've got my two carbons right here, alkyl group and carboxylic acid. And it's the same thing here, just with the twist in this sigma bond. So in the same vein of the malonic ester synthesis, we have the acetoacetic ester synthesis. The difference here is the product form is not going to be a carboxylic acid, but rather still have that ketone that is used in our ethyl acetoacetate, which we will use as our enolate and nucleophile. So in the same fashion as the other one, it's going to go ahead and substitute here in SN2 fashion. It's going to form this product with the R group of our choice in this position. And we're going to go ahead and do some acid workup. Let's use the right color here in order to turn that into a carboxylic acid. But the carboxylic acid is only going to be on one side. The decarboxylation is going to be the same. However, instead, where with our decarboxylation that we showed earlier, you can imagine the only real difference here is it's as if we don't have this right here at all. And it's going to form the same darn thing, except we just lose this extra alcohol here. And you can see how now that we don't have that, we just form the ketone with the R group of our choice. And jumping over here, sure enough, that's what we've formed. Then there's microreactions. I think these are pretty fun because they're a little bit different than what we've been seeing. Typically, when we have the carbonyl, we like to use it as our electrophile. Things like to come in here and hit the electrophile, and we add our R group over into this position. But that's how the Michael is so synthetically useful, is rather that we're going to do a 1,4 addition. And that's why the Michael reactions are so synthetically useful, because now we're going to have the opportunity to do what's called a 1,4 addition or a conjugate addition, because we are using this conjugated pi system in order for us to add a nucleophile into this position right here. which is going to cause these to bump up here, and then this in turn to bump up here. So the question is, what kind of nucleophiles are going to do that for us? And you can go into your books and note that they'll basically spell it out for you. You know, they'll say, these are your Michael donors that you need to remember, and these are your Michael acceptors that you need to remember. Or sorry, Michael acceptors, not receptors. Michael acceptors. You can see I don't really focus too much on this whole memorization concept, because you don't need to memorize this if you just understand the concept behind them. And the concept behind them is the difference between what's going to be a Michael donor and what's going to instead add into this position here, the carbonyl, is you need a stabilized nucleophile. The stabilization of that nucleophile is going to allow that nucleophile to go through the thermodynamic process that is this here. If you have some crazy over-the-top strong nucleophile, say a Grignard, for example, you know, this guy is just going to go. He's not going to wait for anybody, and he's just going to find the nearest carbonyl that he can and hit it. But if we have stabilization, that's going to allow us to go through this thermodynamic process of a Michael conjugate addition. And so what are some examples of some stabilized nucleophiles? Well, you can have enolates, of course. But what's important is, you know, this isn't a stable enolate, as you've learned. This is going to want to form the non-enolate version of this. But if we instead add another carbonyl, now we have a Michael donor. So not so much about memorizing what is and isn't a Michael donor, but rather memorizing or recognizing why this is a Michael donor. If you can do that, then it shouldn't be too difficult for you to recognize when something is or isn't going to do a Michael reaction. Then we have our Michael acceptors, and the basis behind them is all we need is that alpha beta unsaturated pi bond that I was talking about. Alpha and beta because it's in that proximity to a carbonyl. That's the definition of the Michael acceptor, is that alpha beta I can't spell, but you guys get the concept. Unsaturated. Ooh, that's rough. So what are some examples of that? Well, I've drawn one up here, this aldehyde, or of course you could have an ester, you know, why not? Who cares? These are usually formed through the process of an aldol condensation. But there's some uncommon ones, but then there are some that are often missed by students, I've recognized, such as a nitrile, for example, because it's not that standard form that we see. But what's important is we know that this is a carboxylic acid derivative, and any carboxylic acid derivative is going to have that alpha beta positioning, because if we hydrolyze this with acid, you know, that's going to reform the carboxylic acid, and now you can ideally see that alpha beta positioning. Let's go ahead and get rid of that green so we don't confuse. And in that same vein, we have nitro groups, which tend to confuse some, but this also has that alpha beta unsaturated. So all of these are going to be excellent Michael acceptors, and you can imagine the other alternatives that we have here. So I've drawn some examples for us, and I want us to go through these and decide if these are donors or acceptors in regard specifically to a Michael reaction. We are talking only about Michael reactions right now. So if it's a donor or acceptor, I want you to let me know. So the first one we want to look at is this dialkyl cuprate. And hopefully you can recognize that this is indeed going to be a really good Michael donor, because we've got this transitional metal here, which is going to stabilize this nucleophile. So it's going to want to go in a conjugate addition. Now over here, is this a donor and acceptor? And sure enough, this too is a donor. In the same fashion as what we showed earlier, we have a stabilized enolate, and enolates are stabilized nucleophiles. Jumping over here, now this one's a bit of a trick, because this is actually going to be neither. The common mistake is thinking that this will be a Michael donor, but recall again that this isn't actually all that stabilized. Yes, this is an acidic proton, and we can form this, but it's going to require some exceptional circumstances. You know, we need to use LDA to form this enolate, and that's a very strong base. And if we can't easily form it, then it's not going to want to be a Michael donor typically. Jumping over here, The common mistake is to see this nitrile and think, oh, it's an acceptor. But this also is a donor, because we can't miss this lone pair right here. I've just drew the negative charge to highlight it. But don't be so caught up in seeing nitrile and immediately assuming you know what it is. But look at the whole structure. We've got a lone pair. This isn't going to want to be the electrophile. This is going to want to be the nucleophile. I don't know why I numbered this in this fashion, but let's go ahead and jump over to number 5 next. And you tell me, Michael, donor or acceptor? Again, the answer is neither, because I'm a jerk and apparently didn't put a single acceptor on here. That was strange and kind of coincidental. My apologies, but this doesn't have that alpha beta unsaturated pi bond, and so this isn't going to be a Michael acceptor. Or rather, it's just the carbonyls are electrophile. Then we've got lithium aluminum hydride, and you tell me, is this a donor or an acceptor? This also is a common mistake, but this is neither. This 10 times out of 10 is always going to deliver that hydride to the carbonyl. And so if this were a Michael acceptor, it would not bother waiting for this, because this just wants to do something. It's not going to hesitate to deliver to that most electrophilic spot. So jumping back to the Michael reaction, let's go ahead and finish it out. Let's use the commonly used Michael donor, which is that dialkyl cuprate. And what that's going to form is, using this mechanism, we're going to add the nucleophile that we've chosen. When it's cuprate, we're only going to add one of these R groups here. And you can see how this pi bond is going to move into this position, and that negative charge is going to show up over here. And then we're going to use probably an acid workup in order to quench our charges. And what do you know? We're going to form the enol. And as we know, enols, big fans of tautomerization. That's going to go ahead and tautomerize. I never know how to spell that, so I'll send it right there into this structure here. Then there's the storic enamine synthesis, which is really just a follow-up to the Michael. It builds upon the weaknesses of the Michael, in which we have to use those specific stabilized nucleophiles or Michael donors. But you might have some product like this, and you see this section right here, and you're like, oh, I could use a Michael, but the problem is that's not a stabilized nucleophile. That's never going to want to be the Michael donor that I need. And so the storic enamine synthesis solves this, as you can read from the name, by converting this into an enamine. And hopefully you recall, I should get rid of that enolate there. We're going to need a secondary amine in order to form that enamine. If we use a primary amine, we're going to form the imine. So as you've learned from previous chapters, that's going to go ahead and form the enamine that we were just discussing. Alkene, amine, and amine. Finish out that ring there. Sorry, it's kind of ugly. And now we have a stabilized nucleophile. But be aware, this is not a Michael donor, simply by the fact that it is specifically for the storic synthesis. Because enamines are used in the storic synthesis, we do not consider them as Michael donors. And so don't list them as such. They're always just simply stabilized nucleophiles used in the storic enamine synthesis. So if we form the alpha beta unsaturated electrophile that we choose, this is more than willing to go ahead and, because it's so stabilized, to add into that 1,4 conjugate position as we were talking about, which is going to form the imine. I guess technically, because of this positive charge, this is a iminium ion. And draw out the rest of the molecule here. And then we're just going to do some acid workup, which, as you've learned from previous chapters, is going to resolve this structure here into the carbonyl, and it's also going to fix this by tautomerizing it into the carbonyl in that position as well. Then we're going to have some leftovers from the hydrolysis of this structure here. And for this chapter, that's what you need to know for your named reactions.